Good evening, good morning, good afternoon. It's your science teacher, Mr. Greenspan, here to tell you a little bit about the three main laws from Sir Isaac Newton. You may know him as the guy who sat underneath the apple tree and then had an apple fall on his head, and he is kind of the guy who came up with the idea that there might be gravity. Well, he's also, Sir Isaac Newton, the guy who came up with three different laws that we call the laws of motion. And as you know, we're talking about recently about the distance and the time and the speed and the velocity of different things, and we've been practicing measurements, and we're going to keep doing that. And Newton's laws kind of will be talked about in between that, and also we'll be doing a lot of different activities to show each of these different laws in the next week or two or three. So this is going to be a lecture that will kind of take a couple weeks to kind of get through in terms of all the different activities we're going to do. Anyway, they're called Newton's law of motions, and there's three of them, and I'll do each one separately there. One's called the law of inertia, one's called the law of force, and one's called the law of action-reaction, or Newton's third law. And so most people probably know what the Newton's laws are if you've had them before, but a lot of people don't understand what exactly they mean or don't believe it. And so I'm going to go through these, and hopefully you'll agree too. First one, Newton's first law of motion says, and this kind of makes sense, right? Think about people in space. An object at rest, it says, will stay at rest, and an object in motion will keep on going at a constant velocity unless there's a force that somehow acts on it. And then you guys know this because if you drop a ball, you know that it falls because of gravity. Well, if you're in space, for example, and you throw a ball, the ball will just keep on going. There's absolutely no forces that act on it, so it will just keep on going. Technically, it would keep on going forever. The second law is called the law of force, which tells you a little bit about how hard something might hit something else, and that's equal to its mass, which how heavy it is, times how fast it's accelerating. Acceleration is a change in speed. So when you say something's accelerating, it means that it's going from a speed of 60 miles an hour up to a speed of 70, so it's getting faster. And the Newton's third law says that for every action that there exists on an object, there's an opposite reaction. And I'll tell you about that a little bit as we keep going. So here's the first one again, law of motion, which is also called the law of inertia, the first law, that says that an object that stays at rest will stay at rest, and an object in motion will keep going at that same velocity, won't increase or decrease, unless you push it or do some kind of force that acts on it. So, you might be used to driving in a car. If you have somebody hits the brakes, you kind of keep going forward. That's called inertia. It's your body trying to keep going in the same velocity that it was going before. So when you're in a car and somebody slams on the brakes, or if you've ever gotten in a car accident accidentally, that force that kind of keeps making you want to go forward, that's called inertia, the tendency that you have to not want to change your velocity. And this law says that once something is airborne, unless it's acted on by some kind of force like gravity or friction, which we'll talk about, then it will keep going forever. Now that we know that doesn't really happen. If you fall, eventually you stop rolling because of friction with the ground or something like that. But if something was allowed to keep going, it would keep going forever. And so a golf ball, for example, would just sit on a tee all day long unless somebody uses a force with the golf club and swings at it. Then it will obviously move. So this is on your sheet, it says click to add title, but I'm just not doing this as a presentation. But it says, why do we observe everyday objects in motion slowing down and becoming motionless, seemingly without a force? Well, the answer is things slow down even though they don't look like they should slow down, something like a frisbee, and it's because of friction. Usually it's air friction, sometimes it's friction with the ground, and sometimes it's friction with a liquid. And that friction is a resistance that makes it eventually, as you probably know, you stop moving eventually. And objects on Earth, unlike space, as I said, are under the influence of friction all the time. So going down the street, when you walk and your feet are kind of on the sidewalk, even when you slide on some ice, eventually the friction kind of makes you stop. And so that's kind of what the answer is. The answer is the unbalanced force that acts on an object is called friction, and there are different kinds of frictions. There's sliding friction, like ice skating, as I just mentioned, where eventually you're sliding and the friction kind of makes you stop. There's rolling friction, where the object actually keeps traveling around and around and around like a bowling ball. There's fluid or air or liquid friction, which is resistance from water or from air. Think of a frisbee eventually slowing down because the air makes it kind of stop. And then there's static friction, which is kind of friction where it's rubbing against some other surface, kind of like when your feet rub against the carpet. So, of course, if you slid a book and when last watched it kind of go down a table or something, eventually it's going to stop and it's going to slow down, and you won't be able to push it that far because of friction. And if there was no friction, kind of like think about an air hockey table or something like that, if there was no friction, or if it was perfectly never ever having any ice of friction, you just keep on going forever and ever and ever. But that obviously doesn't happen on Earth. Now, what does this mean? This means for you that if you're going in a car that's going 80 miles an hour or whatever, then you're going that speed too. And the inertia, that force that makes you want to keep going forward, is kind of going to be a big deal if you smash into a brick wall. You're going to be smashing at it at 80 miles an hour because that's where your body keeps going. Now, the second law is called the law of force, which says that the hardness that something hits something else, whether it's a car accident or two football players, that it's equal to their mass times their acceleration. So we say it's F is force, and we say that that's equal to M times A, mass times acceleration. So a lot of times we use mass in grams or kilograms. We use acceleration in units that are called meters per second every second, so meters per second per second. All that means is that we're changing a speed every second. So meters per second is a speed, and then divided by seconds again means that we're taking the speed and we're changing it over time. And the unit of force, and I'll go over that more too, and the unit of force is called newtons. We say 1 newton. And usually 1 newton is equal to 1 kilogram that's going at an acceleration of 1 meter per second per second. So give you an example, if you were looking for how much force a 1400 kilogram car that was going at 2 meters per second, you'd say 1400 kilograms, which is the mass, times 2 meters per second squared, which is 1400 times 2, so it's got 2800 newtons of force. And if you look here, this kind of makes sense. Take a look here. Here we've got a force of 10, right? Which is 2 times 5, mass times acceleration. But we can also have that if we took the mass and we make it bigger, then the thing doesn't even barely have to be accelerating. It can be going at what number would this be? This would have to be a 2. So the heavier something is, the more force it gives. Like think of a heavy football player. And the faster something's accelerating also makes a difference. So if you drop a penny and you drop something else heavy from the top of a building, the penny and the thing are going to accelerate at the same rate, but they're going to have different masses, so the force would be a lot harder for something that's heavy as opposed to something like a penny. And don't worry about the numbers here, but this explains why two objects that accelerate at this ground at the same rate, why they don't have the same force, is because they're different masses. So this big rock's going to have much more force, even though technically its acceleration right here, 9.8, is the same in both of these. But when you have a 1 kilogram little rock, that's only going to give 9.8 newtons. If you have a 10 kilogram rock, you're going to have 98 newtons. So it's a lot more force. I think you should try these 3. I'm going to leave them up for a second. There's 4 questions here, and the acceleration is given, and the mass is given, and the all the different variables are given. And so if you're looking for acceleration, you say F equals ma, and you plug in F and you plug in m, and you look for a. So it's just basic algebra. I'm going to leave these up for a second, and then I'll put up the answers, but I think you should still try them. Here's your first one. I'll leave it here for a second. You should pause the video and try to do these. And then here we go. So take a look at this one. The acceleration is 12 newtons, or the force is 12 newtons. The mass is 3 kilograms, so the acceleration must be 4, because 4 times 3 is 12. Here we got 16. We're accelerating at 5 meters per second, and we wanted to find the mass, 3.2, because 3.2 times 5 is 16. You can see the rest of these, and we're going to practice with some of these too. And if you look here, you can think about force being all sorts of things. Gravity is a force between objects. You can think of electricity as being a force of electrons. Magnetism is the force of a magnetic field, and you could think of sports as being the force of friction, pushing and rubbing against the gym floor, or think of the tires on a bike. So these are all examples of different forces. Equals the mass times the acceleration. Third and last law of Newton's laws is that every action has an equal and opposite reaction. So pretend this person here who's sitting down on this chair, Newton's law says that they're pushing their tush down on the chair, and the chair is actually also exerting a force upward on their body. And that sounds kind of weird, but they're called action and reaction forces. Anytime you push on something, there's actually a force that kind of pushes back at you. And those are called action-reaction forces. And you know these very well. The first example I want to give you is of a fish. If you notice, a fish propels itself through the water and it uses its fins. And it pushes the water back, but then it propels forward. Think about a car. The exhaust of the car comes out the tailpipe. It comes out the back of the car, but the car goes forward. So for every action that is in one direction, the object will also have an opposite reaction. Also think of this in terms of force. A heavier fish is going to be more mass, so he's going to actually have more force and push more water than a little fish. And of course, if they change their fin direction and they start paddling forward, then they'll start moving backwards. If you've ever gone boating, you probably know that too. When you want to go backwards in a canoe, you actually have to paddle forward. Another thing about Newton's third law that is a good example are birds. When they fly, they have to push down on the air. The air also then, in return, pushes them up. So at the same time that they're pushing down with their wings, they're getting lift from the air, and it's pushing them up. For every action, there's an opposite reaction. And again, I just mentioned this. I'll let you kind of read this, but it's always an opposite direction for birds when they're flying. Another example, baseball. You go to swing at a baseball. When you hit the baseball with the bat, you're hitting the ball, but the ball is also exerting a force onto the bat too. As weird as that sounds. And again, you've probably seen this with a car too. A car, if you spin the wheels backwards, they kind of grip the road and they'll push the car backwards. Another one that I really like as a good example is a rocket ship or even a car. As you can see that the shuttle here, as the gasoline and all the fuel is burned, it's going to go downwards, but it's going to push the rocket up. So for every action that takes something in one direction, there's an opposite reaction that has to go the other way. Now, I'm about ready to stop, but I wanted to quickly show you, because I do understand that it might be hard, when I'm going over a lot of slides at once. I would watch the movie more than once, think of it like lecture, and then if you go to the ILS Moodle site and you go to measurement and movement, you're going to get to a web link that says PowerPoint presentations right at the top. When you click on that PowerPoint presentation, you're going to get several different things here, but the one that I just showed you is this first one right here that says Newton's Laws of Motion, and when you click on it, it will open. And I'm not going to open it because I already have it open, but it's going to be this PowerPoint. So I hope that you can go back and maybe watch the PowerPoint again, try those questions out, and let me know what I can do to help as we kind of investigate each of these laws a little bit more. Thanks you guys a lot. I know that this is difficult. You're doing a fine job. I really want you to stick with it. You can do it. Thanks a lot. Bye.